Imagine a world where every digital lock, every virtual vault lies exposed. A world where the secrets of nations and the privacy of individuals are as easily accessible as an open book. Sounds like science fiction? Perhaps. But the truth is, we're already living on the edge of that reality. Our modern existence is built upon a foundation of codes. These intricate strings of numbers and letters are the guardians of our digital lives. They shield our bank accounts from theft, protect our personal communications from prying eyes, and safeguard national security from potential adversaries. Think of it as a global digital fortress, seemingly impenetrable. But this fortress has a weakness, a chink in its armor that threatens to bring the entire structure crashing down. The codes we rely on today are mathematical constructs, algorithms that can, in theory, be broken. It's a constant cat-and-mouse game with cryptographers developing ever more complex codes and hackers relentlessly searching for the keys to unlock them. For now, the good guys are mostly winning. But the landscape is shifting. What if a machine emerged, a quantum machine, capable of cracking even the most sophisticated codes in a blink of an eye? This isn't a far-fetched scenario. Scientists around the world are working tirelessly to build just such a machine. It's a race against time, a desperate scramble to find a truly unbreakable shield before our current defenses become obsolete. Consider the implications. Global finance grinds to a halt as banking systems are compromised. Governments collapse as classified information is leaked. Personal lives are exposed as private communications are laid bare. The digital chaos would be unprecedented. But how vulnerable are we really? Think about your daily routine. You wake up, check your email, perhaps make an online purchase. Every one of those interactions is protected by encryption. You trust that those codes are keeping your information safe. But what happens when that trust is misplaced? What happens when the codes we trust can no longer protect us? This is the question that haunts the minds of security experts and keeps governments up at night. The code war is already raging and the stakes have never been higher. Imagine a digital safe, holding the world's most valuable secrets. Now picture a master thief, not with lockpicks and crowbars, but armed with the power to bend the very laws of physics. This isn't a scene from a heist movie, but a looming reality. The rise of the quantum computer. These aren't your everyday desktop machines. We're talking about revolutionary devices that harness the strange and counterintuitive principles of quantum mechanics. They operate on qubits, quantum bits, which, unlike classical bits that are either a 0 or a 1, can exist in a state of superposition, meaning they can be both 0 and 1 simultaneously. This opens up possibilities that were once confined to the realm of science fiction. A quantum computer with enough qubits, millions of them perhaps, could perform calculations that would take even the most powerful supercomputers billions of years to complete. It's like comparing a horse-drawn carriage to a rocket ship. But this unprecedented power comes with a dark side. The very algorithms that allow quantum computers to perform these amazing feats also make them exceptionally good at breaking codes. Specifically, Shor's algorithm, developed in 1994 by mathematician Peter Shor, is a quantum algorithm designed to factor large numbers exponentially faster than the best classical algorithms. This seemingly obscure mathematical breakthrough has profound implications for cybersecurity. Why? Because much of our current encryption relies on the difficulty of factoring large numbers. RSA, for example, one of the most widely used encryption algorithms, depends on the fact that it takes an impractically long time for classical computers to find the prime factors of very large numbers. But a sufficiently powerful quantum computer running Shor's algorithm could crack RSA encryption in a matter of hours, or even minutes. This is not a hypothetical threat. It's a mathematical certainty. Think about the consequences. Global financial systems are protected by encryption. Bank accounts, stock markets, international money transfers, all relying on codes that could be rendered obsolete. Imagine the chaos if cybercriminals could access these systems at will, draining accounts, manipulating markets, and destabilizing the global economy. It's a scenario that keeps finance ministers awake at night, but it's not just about money. National security is also at stake. Governments rely on encryption to protect classified information, military secrets, and diplomatic communications. Quantum computers could potentially decrypt these communications, exposing vulnerabilities and undermining national defense. The balance of power between nations could shift dramatically. Consider the implications for nuclear weapons, intelligence operations, and international relations. The stakes couldn't be higher. Even our personal lives are at risk. Our emails, social media accounts, medical records, and online purchases are all protected by encryption. A quantum computer could unlock these digital vaults, exposing our private information to anyone who wants it. Identity theft, blackmail, and invasion of privacy could become rampant. The erosion of trust in the digital world would be devastating. So, what is being done? Scientists and cryptographers are racing against time to develop new encryption methods that are resistant to quantum attacks. These are known as post-quantum cryptography algorithms designed to withstand the power of quantum computers. It's a complex and challenging task, requiring a fundamental rethinking of how we secure information. The digital apocalypse clock is ticking, but the future isn't set in stone. The race to develop quantum-resistant cryptography is underway, a battle between offense and defense, a struggle to protect our digital world from the coming quantum threat. Are we ready for this new era of cyber warfare? What is the next step in the fight to come? But what if the very fabric of reality held the key to an even more secure future? What if the answer lay not in complex algorithms, but in the bizarre and counterintuitive world of quantum mechanics? Prepare to step through the looking glass because the rules are about to change. We're about to delve into a realm where particles can be in two places at once, where cause and effect become blurred, and where two objects can be linked across vast distances as if by an invisible thread. This isn't science fiction. This is the quantum realm. It's a place that has baffled and fascinated scientists for over a century, and it's now on the verge of revolutionizing cryptography as we know it. Imagine for a moment a coin spinning in the air. Before it lands, it's neither heads nor tails. It's both simultaneously. This, in essence, is superposition, a fundamental principle of quantum mechanics. A quantum bit or qubit can exist in a superposition of states, representing 0, 1, or any combination thereof. This allows quantum computers to perform calculations in a fundamentally different way than classical computers, opening up possibilities that were once thought impossible. But superposition is just the beginning. Things get really weird when we introduce entanglement. Imagine two of those spinning coins, somehow linked together in such a way that when one lands on heads, the other instantly lands on tails, no matter how far apart they are. Einstein famously called this spooky action at a distance, and it's one of the most mind-bending concepts in all of physics. Entanglement means that two quantum particles can be inextricably linked, their fates intertwined regardless of the distance separating them. Measure the state of one particle and you instantly know the state of the other, even if they're light years apart. It's as if they're communicating faster than the speed of light, which, according to Einstein's theory of relativity, shouldn't be possible. This spooky action is what makes the idea of quantum networks possible across the world. So how can these strange quantum properties be harnessed for cryptography? The answer lies in the fact that observing a quantum system inevitably changes it. This is known as the observer effect. Imagine trying to measure the spin of an electron. The very act of measurement disturbs the electron, changing its state. This seemingly inconvenient property can actually be used to our advantage in quantum cryptography. If someone tries to eavesdrop on a quantum communication channel, their attempt to measure the quantum bits will inevitably disturb them, leaving detectable traces. It's like trying to tap a phone line, but every time you try to listen in, the line goes dead. This inherent security, guaranteed by the laws of physics themselves, is what makes quantum cryptography so promising. But to truly appreciate the power of quantum mechanics, one needs to abandon classical intuition. The quantum world operates according to rules that are fundamentally different from the world we experience every day. It's a world of probabilities, uncertainties, and interconnectedness, a world where the act of observation changes reality itself. It is time to rethink everything you thought you knew about our universe and the physics which control it. Are you ready to see what else is in store? But how do we actually use this quantum weirdness to our advantage? How do we translate these abstract concepts into a tangible security system? The answer, perhaps surprisingly, lies in the humble photon, a single particle of light. For centuries, light has illuminated our world, guided our ships, and fueled our art. From the flickering flame of a candle to the blazing intensity of a laser, light has been a constant companion to humanity. But now, light is poised to play a new and crucial role as the key to unbreakable encryption. Think of a single photon as a tiny individual bullet of light, but unlike a classical bullet, this one exists in a world of quantum possibilities. We can control and manipulate the properties of a photon with incredible precision. We can alter its polarization, which is essentially the direction in which it oscillates as it travels. Imagine twisting a tiny dial, precisely aligning the wave of light to a specific angle. This ability to control and measure the polarization of a single photon is the foundation of quantum communication. These aren't just theoretical musings. Labs across the globe have sprung up that look to control this new technology. Scientists are developing sophisticated tools to generate and detect these single photons. Specialized lasers emit light so faint that it can be reliably broken down into individual particles. Highly sensitive detectors stand ready to measure the polarization of each passing photon, teasing out the information encoded within its quantum state. It's a delicate dance between light and matter, a symphony of quantum control. Why photons? Why not use electrons or some other quantum particle? The answer lies in their unique properties. Photons are relatively easy to generate and manipulate. They travel at the speed of light, making them ideal for long-distance communication. And perhaps most importantly, they interact weakly with their environment, meaning they are less susceptible to noise and interference. They are, in essence, the perfect quantum messengers. So, how do we encode information onto these tiny messengers? Think back to the idea of polarization. We can use different polarization angles to represent different bits of information. For example, a photon polarized vertically could represent a 0, while a photon polarized horizontally could represent a 1. But here's where the quantum magic comes in. We can also use diagonal polarizations, 45 degrees or 135 degrees, to represent other states. This is where that superposition property comes into play. It creates a whole new way of encoding information beyond the classical way. This ability to encode information using the quantum properties of photons opens up possibilities that were simply impossible in the classical world. These tiny messengers, these ghost particles, can carry information in ways that are inherently secure, protected by the very laws of physics. Is it a secret? Quantum mechanics is here to save the day, and the future is bright. But what exactly is it that makes this all so secure? It's time to peel back another layer of this quantum onion. We've seen how the quantum realm offers the potential for unbreakable security, wielding photons like secret agents carrying encrypted messages. But what does this all actually mean in practice? It's time to introduce the core concept that could revolutionize how we protect our information: quantum key distribution, or QKD. Now, before you imagine photons themselves scrambling your emails, let's clarify something crucial. QKD isn't about encrypting the message itself using quantum mechanics. Think of it more like the delivery of a super secure key, one so well protected that any attempt to steal it is immediately obvious. That's the essence of quantum key distribution. Our current encryption methods, like the ones protecting your online banking, rely on complex mathematical algorithms. These algorithms are publicly known. The secrecy lies in the key, a long string of numbers that scrambles your data. The problem is, those keys are typically exchanged using those same mathematical algorithms. It's like locking your house with a key that you mailed to yourself in an unlocked box. QKD offers a fundamentally different approach. Instead of using math to protect the key, it uses the laws of physics. Imagine Alice wants to send a confidential file to Bob. Instead of sending the file directly, she uses a QKD system to create a secret key known only to her and Bob. She then uses this key with a traditional encryption algorithm like AES to encrypt the actual file and send it to Bob. Bob, possessing the same key, can then decrypt the file. The beauty of QKD lies in how that initial secret key is created and distributed. It is an absolutely unbreakable key so long as no one else has it. So what makes this secret key so special? It's all thanks to those quantum properties we discussed earlier, specifically the observer effect. Remember, any attempt to measure a quantum system inevitably disturbs it. If Eve, the potential eavesdropper, tries to intercept the photons carrying the key, her attempt to measure their polarization will inevitably alter their state, leaving a detectable fingerprint. Alice and Bob, knowing this, can then compare a portion of their key exchange over a public channel. If they detect any discrepancies, any unexpected errors, they know that someone has been eavesdropping, and they discard the key. It's like a built-in alarm system that warns them of any potential threats. If everything matches up, they can be confident that their key is secure and use it to encrypt their sensitive data. The best thing about this alarm system is that it is not based on software, but the very physics of our universe. Think of it like this. You're handing a delicate object to a friend. If someone tries to snatch it, the object will break, alerting you to the attempted theft. QKD provides a perfectly secure key exchange using quantum mechanics to guarantee that only the intended recipient receives the key. This is because it uses a method that follows the laws of physics, which are nearly impossible to violate. But how does this actually work on a practical level? How do we go from the abstract principles of quantum mechanics to a working security system? That is the next big question. The answer lies in a clever protocol that forms the bedrock of many current quantum security systems. A protocol known as BB84. So we've established that QKD promises perfectly secure key exchange, using quantum mechanics to guarantee that only the intended recipient receives the key. But how does this actually work on a practical level? How do we go from the abstract principles of quantum mechanics to a working security system? That is the question that occupied the minds of two brilliant scientists in the 1980s, Charles Bennett and Gilles Brassard. Their answer, a seemingly simple yet profoundly ingenious protocol, forms the bedrock of many current quantum security systems. It's a blueprint for unbreakable keys, a testament to the power of human intellect, a protocol known as BB84. BB84, named for Bennett and Brassard in 1984, is the first and most famous QKD protocol. Think of it as the Rosetta Stone of quantum cryptography, the key to unlocking a new era of secure communication. At its heart, BB84 relies on the polarization of single photons, those tiny packets of light we discussed earlier. Imagine Alice, our intrepid sender, wants to transmit a secret key to Bob, our equally astute receiver. Alice begins by generating a stream of single photons, each polarized in one of four possible directions: 0 degrees, 90 degrees, 45 degrees, or 135 degrees. These angles weren't chosen at random. They represent two different measurement bases. The 0 and 90-degree polarizations form what's known as the rectilinear basis, while the 45 and 135-degree polarizations form the diagonal basis. Now here's the crucial part. Alice doesn't choose the polarization of each photon deliberately. Instead, she chooses randomly, using a truly random number generator. This is where the quantum randomness comes into play, injecting an element of unpredictability that is essential for security. For each photon, she randomly selects a polarization angle and sends it to Bob. Think of it as Alice sending a series of quantum postcards, each with a randomly chosen picture on the front. Bob, on the receiving end, has no idea which polarization angle Alice used for each photon. So he, too, randomly chooses a measurement basis for each incoming photon, either the rectilinear basis or the diagonal basis. He then uses a polarizer, a special filter that only allows photons with a specific polarization to pass through to measure the polarization of the photon. If Bob chooses the same basis as Alice, he will correctly measure the polarization of the photon. For example, if Alice sends a photon polarized at 0 degrees and Bob measures it using the rectilinear basis, he will correctly measure 0 degrees. But if Bob chooses the wrong basis, he will get a random result. If Alice sends a photon polarized at 0 degrees and Bob measures it using the diagonal basis, he will have a 50% chance of measuring 45 degrees and a 50% chance of measuring 135 degrees. It's like trying to read a sign written in a foreign language. Sometimes you can decipher it. Sometimes you're completely lost. After Alice has sent a sufficient number of photons, she and Bob publicly compare which bases they used for each photon. This is done over a public channel like the Internet, so Eve, our ever-present eavesdropper, can listen in without compromising the security of the key. For the photons, where Alice and Bob used the same basis, they keep the corresponding bit value. For the photons where they use different bases, they discard the bit. This process winnows down the initial stream of photons into a shorter, shared string of bits, a raw key known only to Alice and Bob. But even at this stage, the key may not be perfectly secure. Eve, the eavesdropper, might have tried to intercept some of the photons, potentially introducing errors into the key. So, Alice and Bob perform one final check. They publicly compare a small subset of their shared key. If they find too many errors, it means that Eve has been eavesdropping and they discard the entire key. But if the error rate is low enough, they can be confident that their key is secure and use it to encrypt their messages. The elegance of the BB84 protocol lies in its simplicity and its reliance on fundamental principles of quantum mechanics. It's a testament to the ingenuity of Bennett and Brassard, a blueprint for unbreakable keys that has inspired countless researchers and engineers. It's the elegant dance of quantum randomness that is key to keeping communications secure and only known by those sending and receiving it. But what is it about the nature of quantum mechanics that makes this process so secure? What prevents Eve from simply copying the photons and listening in without being detected? The answer lies in two fundamental principles of quantum mechanics, principles that act as the ultimate security guards, forever protecting our quantum secrets. So, Alice and Bob have this ingenious system for exchanging a secret key, all thanks to the weirdness of quantum mechanics. But what exactly is it about the nature of reality itself that makes this process so secure? What prevents Eve, the ever-present eavesdropper, from simply copying the photons and listening in without being detected? It is time to find out. Imagine trying to sneak a peek at someone's notes during a test. The moment you glance over, they instinctively shield their paper, becoming aware they are being watched. Now, amplify that reaction to the subatomic level where the very act of observation changes the thing being observed. This seemingly inconvenient phenomenon is the bedrock of quantum security. It is known as the observer effect, and it's a cornerstone of quantum mechanics. It dictates that the act of measuring a quantum system inevitably disturbs it. It is not a matter of clumsy equipment or human error. It is a fundamental property of the universe. To understand why it is so important, one must really delve into what this means. Think about it. In the classical world, we can observe things without significantly affecting them. We can watch a ball roll down a hill without altering its trajectory. We can measure the temperature of a room without changing its temperature. But the quantum world doesn't play by these rules. When we try to measure the properties of a quantum particle, such as the polarization of a photon, we have to interact with it. We have to shine light on it, bounce something off of it, or otherwise probe its state. But this interaction inevitably changes the particle. It's like trying to take a photograph of a shy animal. The moment you turn on the flash, it darts away, forever altering the scene you were trying to capture. Any attempt by an eavesdropper to intercept the quantum key photons will leave detectable traces. It is like an unforgeable tamper, evidence seal on a package. If someone tries to open it, there is no way to reseal it without leaving evidence. It is built directly into the universe. This inherent property of quantum mechanics acts as an unforgeable tamper evidence seal. It means that any attempt to measure the quantum key photons will inevitably disturb them, leaving detectable traces that alert Alice and Bob to the presence of an eavesdropper. It is the ultimate security system, one that relies not on complex algorithms, but on the fundamental laws of physics themselves. Perhaps you are asking yourself now, what if Eve, our potential eavesdropper, comes up with a clever way to measure the photons without disturbing them? What if she uses some kind of exotic quantum technology to copy the photons perfectly, without leaving any trace? Sadly for Eve, there's another fundamental principle of quantum mechanics that stands in her way, an unbreakable rule that ensures the security of quantum communication. It is a rule called the no-cloning theorem. So Alice and Bob have this ingenious system for exchanging a secret key, all thanks to the weirdness of quantum mechanics. The observer effect, the principle that the act of measurement inevitably disturbs a quantum system, stands as a powerful sentinel against eavesdropping. But imagine the cunning of a would-be thief, a digital pickpocket named Eve. She might think, why not outsmart the quantum world? Why not devise a device so subtle, so ingenious, that it can perfectly copy a photon without disturbing its delicate quantum state? What if Eve could create a perfect clone, an identical twin of each photon carrying the secret key? She could then measure the clone without altering the original, gleaning the information without alerting Alice and Bob to her presence. It sounds like the perfect crime, a way to circumvent the laws of physics themselves. But here's the catch, the ultimate twist in our quantum tale. Nature has a built-in copy protection mechanism, a fundamental law that throws a wrench in Eve's plans. It is known as the no-cloning theorem, and it's a pillar of quantum security. This theorem, derived from the very foundations of quantum mechanics, states that it is fundamentally impossible to create an identical copy of an unknown quantum state. It isn't a matter of technological limitations or engineering challenges. It is an absolute prohibition, a decree issued by the universe itself. Think of it like trying to perfectly duplicate a snowflake. Each snowflake is unique, with an intricate and complex structure. You might be able to create something that looks similar, but you will never be able to create a perfect replica down to the arrangement of every single water molecule. The quantum world is even more sensitive. Trying to copy a quantum state is like trying to capture a fleeting dream. The moment you try to grasp it, it vanishes, transformed by your very attempt to hold it still. The no-cloning theorem is a profound statement about the nature of reality. It tells us that information encoded in a quantum state is fundamentally different from information in the classical world. In the classical world, we can copy information with impunity. We can make endless copies of a document, a photograph, a song, without degrading the original. But the quantum world is far more precious. Information is a delicate resource inextricably linked to the physical state of the system. It cannot be duplicated without disturbance. What does this mean for our eavesdropper, Eve? It means that she cannot simply copy the quantum key photons without altering the originals. Any attempt to create a clone will inevitably introduce errors, alerting Alice and Bob to her presence. She is caught in a quantum trap, unable to circumvent the laws of physics. The universe itself is conspiring against her. So, the no-cloning theorem stands as a powerful guardian of quantum security, ensuring that our secrets remain safe from prying eyes. It is the ultimate copy protection mechanism, a built-in feature of the quantum world that makes eavesdropping impossible. But even with these powerful defenses, the path to unbreakable quantum communication isn't without its challenges. Building the infrastructure to harness these quantum principles, sending photons over vast distances, requires a whole new level of technological ingenuity. But even with these powerful defenses, the path to unbreakable quantum communication isn't without its challenges. Building the infrastructure to harness these quantum principles, sending photons over vast distances, requires a whole new level of technological ingenuity. Are we talking about stringing quantum wires across continents? Not exactly. The solution, as it often does, lies in adapting existing technology and pushing it to its absolute limit. Picture a high-tech laboratory gleaming with polished steel and the hum of sophisticated machinery. Here, scientists are not just theorists scribbling equations on a blackboard. They are the architects of a new digital age, painstakingly crafting the physical reality of quantum communication. They are constructing what can only be described as a quantum channel. What does that channel look like? The backbone of this quantum channel is something we already rely on for much of our modern communication: optical fiber. These incredibly thin strands of glass, thinner than a human hair, are capable of transmitting vast amounts of data in the form of light. But the quantum challenge is not about blasting a beam of light down a fiber. It is about sending and detecting single photons one at a time. And that is where things get incredibly tricky. Imagine trying to deliver a single ping-pong ball through a mile-long tube, making sure it arrives intact and without any interference. That is the scale of the challenge facing engineers working with quantum communication. These single photons are incredibly fragile, easily disrupted by even the slightest disturbance. Temperature fluctuations, vibrations, even stray electromagnetic fields can alter their delicate quantum state. To overcome these challenges, scientists are building specialized hardware, lasers. Not the kind that light up a rock concert, but highly specialized lasers that can emit light with such precision that it can be reliably broken down into individual photons. Think of it as a quantum sniper rifle targeting individual photons with pinpoint accuracy. Then there are the detectors, devices so sensitive that they can register the arrival of a single photon. These are not your everyday light sensors. They are sophisticated instruments, cooled to near absolute zero to reduce noise and capable of detecting the faintest whispers of light. It is like trying to hear a pin drop in the middle of a hurricane. These detectors are designed to isolate and amplify that faint signal. But the real challenge is not just sending and detecting these single photons. It is about doing it over significant distances. As photons travel through optical fiber, they can be scattered, absorbed, or otherwise lost. The longer the distance, the greater the chance that the signal will degrade. It is like trying to shout a message across a crowded stadium. The further the distance, the harder it is to be heard. This means that early quantum communication systems were limited to relatively short distances, perhaps only a few tens of miles. But the dream of a truly global quantum network requires much more. It requires finding ways to stretch the limits of quantum communication, to send photons across cities, countries, and even continents. How could the problem be solved? What engineering breakthroughs are needed to push this forward? The answers are as surprising as the quantum realm itself. The dream of sending perfectly secure messages across vast distances hinges on one crucial and incredibly frustrating factor: noise. Imagine whispering a secret across a crowded room. The louder the chatter, the harder it is to be heard. Now, shrink that whisper down to a single photon, and that crowded room becomes the entire universe, filled with countless sources of interference. Quantum states are notoriously fragile, incredibly sensitive to environmental disturbances. A stray vibration, A sudden temperature change, even the subtle hum of nearby electronics can wreak havoc on these delicate quantum signals. It's a battle against the background radiation, a constant struggle to maintain coherence in a world determined to disrupt it. This isn't just a technical hurdle. It's a fundamental challenge that must be overcome to make quantum cryptography a practical reality outside the pristine confines of the laboratory. How do you isolate something as ephemeral as a single photon from the chaos of the real world? Scientists are employing a range of ingenious techniques, each designed to shield quantum signals from specific types of interference. Vibration dampening systems, the same technology used to protect sensitive scientific instruments from earthquakes, are crucial for stabilizing quantum experiments. Think of it as building a tiny quantum fortress, insulated from the rumblings of the outside world. Specialized materials are employed to shield the delicate quantum systems from electromagnetic interference, much like a Faraday cage protects electronic equipment from external signals. But shielding alone isn't enough. Even in the most carefully controlled environments, some noise is inevitable. That's where error correction comes in. Quantum error correction is a sophisticated technique that allows scientists to detect and correct errors that occur during quantum communication. It's like having a team of quantum detectives constantly monitoring the signal for any signs of tampering or distortion. One approach involves encoding quantum information in a redundant manner, spreading the information across multiple qubits. This is similar to adding extra check bits to a classical data transmission, allowing for the detection and correction of errors. However, quantum error correction is far more complex than its classical counterpart. The no-cloning theorem, that fundamental law of quantum mechanics that prevents perfect copying, also complicates the process of error correction. You can't simply make copies of the quantum state to check for errors, as that would violate the laws of physics. Scientists are exploring a variety of quantum error correction codes, each with its own strengths and weaknesses. Surface codes, for example, are particularly promising for their ability to tolerate relatively high error rates. Topological codes offer inherent robustness against certain types of noise. It's an ongoing arms race, with researchers constantly developing new and more effective error correction techniques. Achieving reliable quantum communication requires constant innovation, a relentless pursuit of new materials, new technologies, and new algorithms. It's a collaborative effort, bringing together physicists, engineers, and computer scientists from around the world. They are pushing the boundaries of what's possible, driven by the promise of a future where information is truly secure. This is not just about building better encryption. It's about fundamentally changing the way we communicate, creating a world where privacy is guaranteed by the very laws of physics. This brings us to another problem. Can we do it at long distances? Even with sophisticated shielding and error correction, the inherent limitations of sending photons through optical fiber loom large. Imagine trying to send a signal across the Atlantic Ocean using only signal flags. The curvature of the Earth, the weather, the sheer distance would make it nearly impossible. Early quantum communication systems faced a similar dilemma. The further a photon travels, the greater the chance it will be lost or altered, effectively limiting the range of secure communication. Early systems could only transmit a reliable quantum key over distances of perhaps 60 or 70 miles. This is sufficient for secure communication within a city, but what about across a state, across a country, or across the ocean? How could scientists overcome this seemingly insurmountable obstacle? One of the earliest and most straightforward solutions was to employ what are known as trusted nodes. Think of these as digital relay stations. Instead of sending the quantum key directly from Alice to Bob, the key is sent in segments, hopping from one trusted node to the next. Alice sends a key to the first node decrypts it and then re-encrypts and sends it to the next node, and so on until it finally reaches Bob. This approach extends the overall distance of the quantum communication link, but it comes with a significant caveat. Each node must be absolutely secure. If even one node is compromised, the entire system is vulnerable. It's like building a chain of fortresses. The chain is only as strong as its weakest link. The security of the entire network depends on the trustworthiness of each individual node. This approach may be acceptable for highly secure government or military communications, but it is less practical for wider-scale deployment. Imagine trusting a series of internet service providers to handle your most sensitive financial data. But what if there was a way to extend the range of quantum communication without relying on trusted nodes? What if there was a way to amplify the quantum signal without disturbing its delicate quantum state? That is where quantum repeaters come in. These are one of the most promising and challenging technologies in the field of quantum communication. Quantum repeaters are devices that can extend the distance of quantum communication by using entanglement swapping and quantum error correction. They do not simply amplify the signal like a classical repeater. Instead, they use quantum entanglement to create a new, stronger link between distant locations. It is difficult to overstate the difficulties in constructing these machines. Imagine trying to build a perfectly functioning clock using parts that are constantly vibrating and interacting with the environment. That is the scale of the challenge facing scientists working on quantum repeaters. Early prototypes of quantum repeaters are large, complex, and extremely sensitive to external disturbances. They require sophisticated control systems, ultra-cold temperatures, and incredibly precise timing. But the potential rewards are enormous. A working quantum repeater would be a game changer, allowing for secure quantum communication across thousands of miles, even across entire continents. Scientists around the world are pushing the boundaries of what is possible, exploring new materials, new architectures, and new protocols for building quantum repeaters. They are driven by the dream of a truly global quantum network, a network that could revolutionize everything from banking and healthcare to national security and scientific research. This vision is pushing scientists to create the next breakthrough, but some are looking up, far past the bounds of our planet. But even with all these ingenious techniques, the Earth itself presents a hurdle. The curvature of the planet, dense cloud cover, and atmospheric interference can all wreak havoc on fragile quantum signals traveling through optical fibers. What if, instead of battling the Earth's limitations, we could simply bypass them? What if we could send quantum keys directly through the vacuum of space, where photons can travel unimpeded, unburdened by the noisy terrestrial environment? It sounds like science fiction, but the race to unlock the potential of quantum communication in space is already underway. Imagine a network of satellites orbiting the Earth, acting as quantum guardians, beaming perfectly secure keys across continents. This isn't just a pipe dream. Scientists have long recognized the potential of space-based quantum communication. The vacuum of space offers a unique advantage, a near-perfect transmission medium for photons. There's virtually no atmosphere to scatter or absorb the light, allowing quantum signals to travel vast distances with minimal loss. But building a quantum satellite is no easy feat. It requires packing all the delicate components of a quantum communication system, the single photon sources, the highly sensitive detectors, into a robust, space-worthy package. These satellites must withstand the harsh environment of space, the extreme temperatures, the intense radiation, and the constant bombardment of micrometeorites. One nation has already taken a bold leap into this new frontier: China. In 2016, they launched Mikius, the world's first quantum communication satellite, named after a 5th century BC Chinese philosopher and scientist. This wasn't just a symbolic gesture. Mikius was a fully functional quantum laboratory in space, designed to test the feasibility of intercontinental quantum key distribution. Mikius demonstrated the power of space-based quantum communication. It successfully transmitted quantum keys between China and Europe, proving that secure communication across the globe was not just a theoretical possibility, but a tangible reality. The satellite utilized a technique called entangled photon distribution, where pairs of entangled photons are generated on the satellite and sent to ground stations on different continents. By measuring the entangled photons, scientists were able to establish a shared secret key protected by the fundamental laws of quantum mechanics. This achievement sparked a new space race, a race not for territory or resources, but for quantum supremacy. Nations around the world are now investing heavily in space-based quantum communication programs, recognizing its strategic importance for national security and economic competitiveness. What does this mean for the future? Secure communications across the globe is now within reach, but it is only the first step. The implications are far-reaching, not just for governments but for businesses and for individuals as well. The quantum revolution is expanding to new frontiers. With satellites now acting as celestial guardians beaming down the promise of unbreakable encryption, it's tempting to think the quantum security revolution is complete. The key, it seems, is locked down. But what if securing the key is only half the battle? What if we could use quantum mechanics to protect not just the key, but the entire message itself? Beyond QKD, a thrilling new vista opens, showcasing quantum-powered tools that promise to redefine digital security in ways we are only beginning to imagine. Quantum digital signatures. Imagine a digital signature so secure, so intrinsically linked to the document it authenticates that it's impossible to forge. Forget cryptographic algorithms that can be cracked by future supercomputers. This is a signature forged in the very fabric of quantum reality. How is it possible? Think of it like this. Instead of using a classical signature, which can be copied and pasted, a quantum digital signature uses a unique quantum state to authenticate a document. This quantum state is created by the sender and linked to the document in a way that is impossible to replicate without possessing the original quantum key. Any attempt to tamper with the document or the signature will inevitably alter the quantum state, rendering the signature invalid. It's like trying to reproduce a priceless painting. You might be able to create a convincing imitation, but the subtle brushstrokes, the unique texture of the paint, the very essence of the original will be missing. A quantum digital signature is the digital equivalent of that irreplaceable masterpiece. But the implications extend far beyond simply verifying the authenticity of a document. Quantum digital signatures could revolutionize everything from online voting to intellectual property protection. Imagine a world where every digital transaction is secured by an unforgeable quantum signature where fraud is virtually impossible. It is a world where trust is not based on complex algorithms, but on the immutable laws of physics. And that's not all. Beyond QKD and quantum digital signatures lies another tantalizing prospect: quantum secure direct communication. Can a message be sent, not just securely, but so securely that it cannot be intercepted and read, even by the most powerful eavesdropper? Imagine sending a secret message directly to your recipient, without ever having to encrypt it. This is not science fiction. Quantum secure direct communication utilizes the principles of quantum entanglement and superposition to transmit information directly, without the need for a key. It's like sending a message encoded in the quantum state of a particle. The act of intercepting the message inevitably destroys the quantum state, making it impossible for an eavesdropper to read the information without alerting the sender and receiver. It's a bold idea, a radical departure from traditional cryptography. It means that sensitive information can be transmitted with absolute confidence, even in the presence of sophisticated adversaries. Think of the possibilities. Secure communication between governments, intelligence agencies, and financial institutions, all protected by the ultimate quantum shield. But these are still early days. Quantum digital signatures and quantum secure direct communication are still in the realm of research and development. Scientists and engineers are working tirelessly to overcome the technical challenges, to build the hardware and software needed to bring these technologies to life. The field is constantly evolving, with new protocols and new possibilities emerging all the time. It is a dynamic and exciting area of research, driven by the promise of a future where information is truly secure. Are there other possibilities we haven't even begun to explore yet? What other applications of quantum phenomena will transform our world? The quantum revolution is far from over. In fact, it may have only just begun. Even as scientists push the boundaries of quantum cryptography, a shadow looms. It's a shadow cast not by technical limitations or engineering challenges, but by a theoretical threat, a specter that haunts the halls of cybersecurity. What happens when quantum computing, the very technology that promises unbreakable encryption, becomes the ultimate code breaker? The answer lies in understanding the profound implications of an algorithm conceived in 1994 by a mathematician named Peter Shor. Shor's algorithm. The very name sends shivers down the spines of cryptographers worldwide. You may ask yourself why. Well, it represents a quantum recipe for factoring large numbers exponentially faster than any classical computer can ever hope to achieve. Factoring, you might wonder, what does that even mean? In its simplest form, factoring is like finding the building blocks of a number, breaking it down into its prime number components. For example, the number 15 can be factored into 3 times 5, both prime numbers that can only be divided by themselves, and 1. Seemingly a simple mathematical concept, but this simplicity hides a devastating potential. RSA, or Rivest-Shamir-Adleman, is one of the most widely used encryption algorithms in the world today. From online banking to e-commerce, RSA is the workhorse that keeps our digital world secure. This ingenious algorithm relies on one crucial assumption. It is computationally difficult to factor large numbers. In other words, with RSA, the key to the digital safe is the product of 2 very large prime numbers, each hundreds of digits long. Finding these prime numbers is easy. Multiplying them together is child's play. But factoring the product to retrieve those original prime numbers is another story altogether. With classical computers, the task becomes astronomically more difficult as the numbers get larger. It is like searching for a single grain of sand on every beach on Earth. That's where Shor's algorithm comes in. On a quantum computer, this algorithm provides a shortcut to solving the factoring problem. Imagine a vast maze with only one path to the exit. A classical computer can only explore one path at a time, slowly and painstakingly searching for the solution. A quantum computer, however, can explore all paths simultaneously, thanks to the principles of superposition and quantum entanglement. With Shor's algorithm, a quantum computer can factor numbers exponentially faster, effectively turning a calculation that would take a classical computer billions of years into a task that can be completed in mere hours or even minutes. The implications of this are nothing short of earth-shattering. Picture a world where every RSA encrypted communication, every financial transaction, every government secret is laid bare. It is like the collapse of a digital dam, unleashing a torrent of chaos and vulnerability. The foundations of modern internet security are vulnerable, and the digital apocalypse clock is ticking. What can be done to counter this quantum threat? That is the billion-dollar question that has spurred a global race to develop quantum-resistant cryptography. The quest to find new algorithms that can withstand the power of Shor's algorithm and protect our digital future is in full swing, with scientists, engineers, and mathematicians working around the clock to prepare for a world where the once unassailable fortress of RSA crumbles before our eyes. It is a challenge of epic proportions, and the future of our digital world hangs in the balance. But perhaps there are more angles to consider. Even as scientists push the boundaries of quantum cryptography, a shadow looms. It's a shadow cast not by technical limitations or engineering challenges, but by a theoretical threat, a specter that haunts the halls of cybersecurity. What happens when quantum computing, the very technology that promises unbreakable encryption, becomes the ultimate code breaker? The answer lies in understanding the profound implications of an algorithm conceived in 1994 by a mathematician named Peter Shor. Shor's algorithm, The very name sends shivers down the spines of cryptographers worldwide. You may ask yourself why. Well, it represents a quantum recipe for factoring large numbers exponentially faster than any classical computer can ever hope to achieve. Factoring, you might wonder, what does that even mean? In its simplest form, factoring is like finding the building blocks of a number, breaking it down into its prime number components. For example, the number 15 can be factored into 3 times 5, both prime numbers that can only be divided by themselves, and 1. Seemingly a simple mathematical concept, but this simplicity hides a devastating potential. RSA, or Rivest-Shamir-Adleman, is one of the most widely used encryption algorithms in the world today. From online banking to e-commerce, RSA is the workhorse that keeps our digital world secure. This ingenious algorithm relies on one crucial assumption. It is computationally difficult to factor large numbers. In other words, with RSA, the key to the digital safe is the product of 2 very large prime numbers, each hundreds of digits long. Finding these prime numbers is easy. Multiplying them together is child's play. But factoring the product to retrieve those original prime numbers is another story altogether. With classical computers, the task becomes astronomically more difficult as the numbers get larger. It is like searching for a single grain of sand on every beach on Earth. That's where Shor's algorithm comes in. On a quantum computer, this algorithm provides a shortcut to solving the factoring problem. Imagine a vast maze with only one path to the exit. A classical computer can only explore one path at a time, slowly and painstakingly searching for the solution. A quantum computer, however, can explore all paths simultaneously thanks to the principles of superposition and quantum entanglement. With Shor's algorithm, a quantum computer can factor numbers exponentially faster, effectively turning a calculation that would take a classical computer billions of years into a task that can be completed in mere hours or even minutes. The implications of this are nothing short of earth-shattering. Picture a world where every RSA encrypted communication, every financial transaction, every government secret is laid bare. It is like the collapse of a digital dam, unleashing a torrent of chaos and vulnerability. The foundations of modern internet security are vulnerable, and the digital apocalypse clock is ticking. What can be done to counter this quantum threat? That is the billion-dollar question that has spurred a global race to develop quantum-resistant cryptography. The quest to find new algorithms that can withstand the power of Shor's algorithm and protect our digital future is in full swing, with scientists, engineers, and mathematicians working around the clock to prepare for a world where the once unassailable fortress of RSA crumbles before our eyes. It is a challenge of epic proportions, and the future of our digital world hangs in the balance. But perhaps there are more angles to consider. Quantum key distribution, or QKD, promises unbreakable security, a shield forged in the very laws of physics. But is it truly invincible? Can this seemingly perfect defense be cracked, not by brute force, but by subtle manipulation, by exploiting the imperfections of the real world? The theoretical foundations of QKD are solid, as unshakable as the laws of quantum mechanics themselves. But as any engineer knows, the devil is always in the details. Perfect theory meets imperfect reality, and that's where vulnerabilities can emerge. Imagine building a fortress with walls of solid steel, only to discover that a tiny crack in the foundation allows the enemy to slip inside. These cracks in the quantum armor are known as side-channel attacks. They don't target the core encryption algorithm directly, but instead exploit weaknesses in the hardware or implementation of the QKD system. Think of it as attacking the messenger, not the message. Side-channel attacks are often ingenious, exploiting subtle physical phenomena to glean information about the secret key. One common type of side-channel attack targets the single photon detectors used in QKD systems. These detectors are incredibly sensitive, but they are not perfect. they may have slight variations in their response to different polarizations of light. An attacker could exploit these variations to learn which polarization was used to encode each bit of the key, effectively bypassing the quantum security altogether. It's like trying to guess the combination to a safe by listening to the faint clicks of the tumblers. Another type of side-channel attack targets the timing of the photons. By precisely measuring the arrival time of each photon, an attacker can potentially infer information about the random number generator used to select the polarization. This is like eavesdropping on a conversation by measuring the subtle pauses and inflections in the speaker's voice. Implementation loopholes can also create vulnerabilities. For example, if the random number generator used in the QKD system isn't truly random, an attacker could potentially predict the sequence of polarization angles, compromising the security of the key. Maintaining the unbreakable promise of QKD requires rigorous testing and constant vigilance against new attack vectors. It is a continuous battle between the defenders and the attackers, a constant race to identify and patch vulnerabilities before they can be exploited. Security experts must constantly probe the system for weaknesses, simulating real-world attacks to identify potential loopholes. It's like stress testing a bridge to ensure it can withstand the weight of heavy traffic. One must rigorously test the hardware, analyzing the performance of the single photon detectors and other critical components. One must also verify the randomness of the random number generators and ensure that the implementation of the QKD protocol is flawless. The promise of quantum security is not a guarantee. It is a challenge, a commitment to continuous improvement and unwavering vigilance. As technology evolves, it will reveal new vulnerabilities and new attacks. The price of perfect security is eternal vigilance, and the quantum world is no exception. It is a constant battle to keep QKD secure. What about real-world applications? But even the most meticulously designed quantum defenses, fortified against side-channel attacks and implementation loopholes, remain a theoretical promise until they are put to the test in the real world. Are we ready to trade our mathematically complex encryption algorithms for quantum networks? Is quantum key distribution a technology of the future, or is it ready for today's problems? The answer is unfolding right now, not in academic journals or government white papers, but in the bustling streets and hidden server rooms of cities around the globe. It's time to go behind the scenes and witness the dawn of the quantum age. Forget gleaming labs and pristine research facilities. The true proving ground for quantum cryptography lies in the messy, unpredictable world we all inhabit. Picture technicians in Geneva, Switzerland, carefully splicing quantum equipment into the existing fiber optic network, not as a hypothetical exercise, but as a mission-critical operation. Why Geneva? Because this city, a global hub for diplomacy and finance, was among the first to embrace the potential of quantum security. Here, government agencies, financial institutions, and even some forward-thinking private companies are quietly building a quantum network, a secure backbone for their most sensitive communications. Think of it as a quantum digital fortress, protecting everything from state secrets to high-value financial transactions. Across the globe, in the sprawling metropolis of Tokyo, Japan, a similar story is unfolding. Imagine engineers navigating the crowded streets, installing quantum key distribution systems in banks and telecommunications companies. Japan, a nation renowned for its technological innovation, has been a leader in quantum research for decades. And now, they are translating that research into practical applications, building quantum networks that are designed to protect their critical infrastructure from cyber attacks. Why Tokyo? Because the Japanese government sees quantum technology as essential to their national security and economic competitiveness, and perhaps more than most countries, is aware of the challenges of earthquake-proofing these cutting-edge, sensitive devices. Even in the heart of Washington District of Columbia, a city synonymous with power and secrecy, a quantum revolution is taking place. Picture government officials and cybersecurity experts gathering in windowless rooms. discussing the implementation of quantum key distribution systems in federal agencies. Washington District of Columbia, the nerve center of the United States government, is acutely aware of the growing threat posed by quantum computers. And they are taking steps to prepare for the quantum future, investing heavily in quantum research and development and deploying quantum networks to protect their most sensitive data. These early adopters aren't just experimenting with quantum cryptography, they are relying on it to protect their most valuable assets. These pioneering networks provide invaluable data, insights that are helping to refine the technology and pave the way for wider adoption. They're discovering the real-world challenges of deploying and maintaining quantum systems, the unexpected quirks and limitations that don't show up in the lab. The future is quietly being built, one secure link at a time, and the lessons learned in these early deployments will shape the security landscape for decades to come. Early adopters have provided many lessons. The most important one, perhaps, is simply, what does all of this cost? The quantum security era has definitively begun, promising a fundamental shift in how we protect information. But even as these quantum networks begin to emerge from the lab and into the real world, a crucial question hangs in the air. Can we actually afford this seemingly perfect security? Quantum cryptographic hardware is currently expensive and complex, pushing the price tag far beyond what most organizations, let alone individuals, can realistically consider. Think of a custom-built Formula One race car. The engineering is exquisite, the performance unparalleled, but the cost is astronomical. Early quantum key distribution systems are much the same. Each component, from the single photon sources to the ultra-sensitive detectors, is a marvel of engineering, pushing the limits of what is technologically possible. But this technological sophistication comes at a steep price. What are the economic factors influencing the adoption of quantum technology? Consider the cost of the specialized materials. The crystals used to generate single photons, the exotic alloys needed to build ultra-cold detectors, all come with a hefty price tag. Then there is the cost of the specialized manufacturing processes. Building quantum hardware requires a level of precision and control that is simply not possible with conventional manufacturing techniques. Every component must be carefully crafted and tested, adding to the overall cost. Perhaps the biggest economic hurdle is the cost of deployment and maintenance. Installing a quantum key distribution system requires specialized expertise and infrastructure. The quantum channel, whether it's optical fiber or a satellite link, must be carefully configured and maintained to ensure optimal performance. And because quantum systems are so sensitive to environmental disturbances, they require constant monitoring and maintenance. When will quantum security become affordable and accessible for businesses and individuals? The answer, like the quantum world itself, is uncertain. The path to widespread deployment involves scaling production and reducing costs. As demand for quantum security increases, manufacturers will be able to produce components at a lower cost, taking the principles of economies of scale and applying them to quantum technology. It's like the early days of personal computers. The first personal computers were expensive and clunky, affordable only to the wealthiest hobbyists. But as demand grew and manufacturing processes improved, the cost of personal computers plummeted, making them accessible to everyone. The development of integrated quantum photonics could also dramatically reduce the cost of quantum hardware. Instead of building quantum systems from discrete components, scientists are working to integrate all the necessary elements onto a single chip. This would not only reduce the size and complexity of quantum systems, but also lower the cost of manufacturing. Perhaps surprisingly, the biggest catalyst for reducing quantum costs may come from competition. As more companies enter the quantum security market, they will be driven to innovate and offer more affordable solutions. It's like the cell phone industry. In the early days, only a few companies dominated the market, and cell phones were expensive and unreliable. But as more companies entered the market, prices fell and quality improved. But it is not just about the economics of quantum cryptography. There is also a philosophical question to consider. How much is perfect security worth? Is it worth paying a premium for a technology that promises to protect our most sensitive information from even the most sophisticated adversaries? The answer, of course, depends on the value of the information being protected. For governments and financial institutions that handle highly sensitive data, the cost of quantum security may be a small price to pay for the peace of mind it provides. But for individuals and small businesses, the cost may be prohibitive. What will the balance be? Can quantum systems ever be cheap enough to be accessible to the masses, or will there always be a premium to pay for perfect security? Imagine a tiered system of security, where different levels of protection are available at different price points. The most sensitive data, such as state secrets and high-value financial transactions, could be protected by quantum cryptography. Less sensitive data, such as personal emails and social media posts, could be protected by classical cryptography. It's like the security system in a modern skyscraper. The most valuable tenants on upper floors will have to pay more for that high-level security. The future of quantum security is uncertain. But one thing is clear: the race to make quantum security affordable and accessible is just beginning. What other new economic pressures or unforeseen consequences lay ahead? But as these quantum systems edge closer to ubiquity, a much larger question emerges, one that transcends mere economics and dives deep into the heart of geopolitics. In a world where unbreakable codes are within reach, who will control the keys to the quantum kingdom? Imagine a digital arms race, not of bombs and missiles, but of qubits and quantum algorithms. Nations across the globe are now locked in a fierce competition to achieve quantum supremacy, a position of dominance in the development and deployment of quantum technologies. This isn't just about bragging rights. It's about national security, economic competitiveness, and the future balance of power in the 21st century. It is the high-stakes game of quantum poker. What are the strategies and the hands being played? Massive government investments are fueling this quantum frenzy, with countries like China, the United States, and the European Union pouring billions of dollars into quantum research and development. These aren't just small grants to university labs. We're talking about strategic initiatives, national programs designed to accelerate innovation and build a quantum-ready workforce. China, for example, has made quantum technology a top priority in its national science and technology agenda, investing heavily in research, infrastructure, and talent development. Their Messias satellite, the world's first quantum communication satellite, was just the opening move in a much larger game. Think of it as China raising the stakes, signaling its intention to be a major player in the quantum arena. The United States, not to be outdone, has launched its own National Quantum Initiative, a multi-agency effort to accelerate quantum research and development across government, academia, and industry. It is a concerted push to maintain America's technological leadership in the face of growing competition. The European Union is also in the game with its Quantum Technologies flagship, a €1 billion initiative designed to foster collaboration and innovation across Europe. The EU is aiming to build a strong and competitive quantum industry, ensuring that Europe remains at the forefront of this technological revolution. But it's not just about money, it's about talent. The global quantum race is also a talent war, a competition to attract and retain the world's leading quantum scientists and engineers. Universities, research institutions, and companies are all vying for the best and brightest minds in the field, offering lucrative salaries, cutting-edge research facilities, and the opportunity to work on groundbreaking projects. This is especially so in places like the University of Waterloo in Canada. This global race accelerates innovation, driving researchers to push the boundaries of what is possible. The pressure to achieve breakthroughs, to develop new quantum algorithms, new quantum materials, and new quantum devices is intense. It is like the space race of the 1960s, a competition that spurred unprecedented innovation and led to technological advancements that continue to benefit us today. But this intense competition also raises geopolitical questions. Who will control the intellectual property rights to quantum technologies? Who will set the standards for quantum communication and security? Who will have the power to shape the future of this transformative technology? Some worry that this quantum race could lead to a new form of technological divide, where a few nations control the keys to the quantum kingdom, leaving others behind. It is a concern that is fueling calls for greater international cooperation and collaboration to ensure that the benefits of quantum technology are shared by all. But such cooperation may be difficult to achieve in a world of increasing geopolitical tensions. The quantum race is not just about technology. It's about power, influence, and the future of the global order. The game is afoot, and the stakes are higher than ever, and with all that is being built, who exactly will lead the quantum revolution? But even as the world's superpowers jostle for position in the quantum arena, a fundamental question remains. Is quantum cryptography the only path to a secure future? Is it the ultimate unbreakable shield against the looming threat of quantum computers? Or are there other approaches, other strategies that could offer a more practical, a more cost-effective, or even a more secure solution? Consider this. While quantum key distribution promises cryptographic keys protected by the laws of physics, it is not a plug-and-play replacement for all our existing security systems. It is complex, it is expensive, and it requires specialized hardware and infrastructure. It is also, at its heart, a key exchange mechanism. The actual encryption of the data still relies on classical algorithms. What if those classical algorithms themselves could be made resistant to quantum attacks? What if we could develop new mathematical codes, new software solutions that could withstand the power of Shor's algorithm and other quantum threats? This is the promise of post-quantum cryptography, also known as PQC. It is a parallel path to security, a different approach to protecting our digital world from the coming quantum storm. Post-quantum cryptography is not about harnessing the weirdness of quantum mechanics. It is about developing new classical algorithms that are designed to be inherently resistant to quantum attacks. These algorithms rely on mathematical problems that are believed to be difficult for both classical and quantum computers to solve, providing a robust and long-lasting defense against cyber attacks. Think of it like building a new kind of lock, a lock so complex and intricate that even a quantum computer would struggle to pick it. These new locks draw their strength from a variety of mathematical disciplines, including lattice-based cryptography, code-based cryptography, and multivariate cryptography. Each approach offers its own unique strengths and weaknesses, its own set of trade-offs between security, performance, and implementation complexity. For example, lattice-based cryptography is considered one of the most promising approaches, offering a high level of security and relatively good performance. It relies on the difficulty of solving certain problems in high-dimensional lattices, mathematical structures that are notoriously difficult for quantum computers to unravel. Code-based cryptography draws its strength from the theory of error-correcting codes. These codes are designed to detect and correct errors that occur during data transmission, but they can also be used to create encryption algorithms that are resistant to quantum attacks. Multivariate cryptography relies on the difficulty of solving systems of multivariate polynomial equations, mathematical problems that are believed to be extremely challenging for both classical and quantum computers. But there are trade-offs. Post-quantum algorithms are typically more computationally intensive than the classical algorithms they are designed to replace. This means that they may require more processing power and memory, potentially impacting performance and battery life. There is also the risk that a new quantum algorithm could be discovered that breaks these post-quantum codes. While researchers have put their greatest minds to the test, there always remains a risk. That possibility keeps cryptographers up at night, constantly searching for new vulnerabilities and developing even stronger defenses. So is one method superior to another? Both quantum key distribution and post-quantum cryptography have their own strengths and weaknesses. Quantum key distribution offers the promise of unbreakable security, but it is complex, expensive, and requires specialized hardware. Post-quantum cryptography offers a more practical and cost-effective solution, but it relies on mathematical assumptions that could be challenged in the future. Securing the future likely requires a combination of strategies, a layered approach that leverages the strengths of both quantum and post-quantum cryptography. Imagine a digital fortress with multiple layers of defense. Quantum key distribution could be used to protect the most sensitive data, while post-quantum cryptography could be used to protect less critical information. Think of quantum key distribution as the vault at the heart of the fortress, protecting the crown jewels. Post-quantum cryptography would be the outer walls, providing a robust defense against more conventional attacks. What happens when these technologies and strategies go through stress tests? How do the brilliant minds behind them make sure both are secure? And where do we go from here? Even with all the ingenious security protocols and post-quantum cryptographic solutions under development, the digital landscape remains a battlefield, a constant tug-of-war between those who seek to protect information and those who seek to exploit it. But what if the ultimate victory wasn't just about building stronger walls, but about fundamentally changing the very nature of the digital world itself? What if instead of just securing the existing internet, we could build a new one, an internet secured by the unyielding laws of quantum physics? Forget everything you think you know about the internet, about packets of data traveling across wires, about servers and routers and the endless stream of information flowing around the globe. Imagine instead a network where information is not just transmitted, but teleported, where security is not just a feature but a fundamental property of the network itself. It is the vision of the quantum internet, a global network where quantum computers, quantum sensors, and quantum communication devices are seamlessly interconnected, a digital realm where the impossible becomes reality. This isn't just about faster downloads or more secure emails. It's about unlocking entirely new possibilities, about revolutionizing fields ranging from medicine and material science to artificial intelligence and space exploration. Think of it as the Internet 2.0, a network that not only connects people but also connects quantum devices, enabling them to work together in ways that were previously unimaginable. This interconnected quantum world promises revolutionary capabilities that will likely change the very fabric of our society. What will this interconnectedness unlock? Imagine a global network of quantum sensors capable of detecting everything from gravitational waves to subtle changes in the Earth's magnetic field. This network could provide early warning systems for earthquakes, tsunamis, and other natural disasters, saving countless lives. Imagine quantum computers collaborating on complex scientific problems such as designing new drugs, developing new materials, or modeling climate change. These quantum simulations could accelerate scientific discovery by orders of magnitude, leading to breakthroughs that would otherwise take decades to achieve. Imagine quantum communication networks spanning the globe, enabling secure and private communication between governments, businesses, and individuals. These quantum links would be immune to eavesdropping, guaranteeing the confidentiality of sensitive data. One may ask, is this simply an upgraded version of the Internet, or are we talking about something on an entirely different level? The quantum internet is not just about faster communication and increased security. It's about creating an entirely new paradigm for how we interact with information, how we collaborate with each other, and how we explore the universe. This also has the potential to offer possibilities we cannot even fathom. Consider the implications for artificial intelligence. Quantum computers could accelerate the development of artificial intelligence algorithms, leading to breakthroughs in machine learning, natural language processing, and computer vision. Imagine artificial intelligence systems that can learn and adapt at quantum speeds, solving complex problems that are currently beyond the reach of even the most powerful supercomputers. Consider also the possibilities for space exploration. Quantum sensors could be used to detect dark matter and dark energy, unlocking the secrets of the universe. Quantum communication networks could enable secure communication with spacecraft on distant planets, paving the way for future interstellar missions. This is the vision that drives researchers to lay the groundwork for the next Internet era. It's not an easy task. Building a quantum Internet requires overcoming a number of formidable technical challenges, from developing stable and reliable quantum devices to building the infrastructure needed to connect them. It is, without a doubt, a long road ahead, but perhaps closer than one might think. What will our reality look like when it has been constructed? And will it be a better reality? As incredible as it sounds, we are now poised to construct an entirely different level of global communications network. But to truly revolutionize an era, we must ask ourselves, who are the minds behind it all? What drives these individuals who dedicate their lives to unlocking the secrets of the quantum realm, pushing the boundaries of what is technologically possible? They are not merely scientists and engineers, but visionaries, pioneers charting a course into uncharted territory. Imagine a young Charles Bennett, captivated by the mysteries of information theory, scribbling equations on a napkin in a New York City pizza parlor. He wasn't just trying to solve a mathematical problem. He was laying the foundation for a revolution in cryptography, the BB-84 protocol, a system now utilized across the world. Consider Gilles Brassard, his intellectual partner, a brilliant computer scientist who dared to challenge the conventional wisdom of the 1980s, at a time when most believed that quantum mechanics was confined to the realm of esoteric physics, not something that could have real-world applications. These individuals are not just names in a textbook. They are the architects of our quantum future, the unsung heroes of the digital age. But what drove them to dedicate their lives to this pursuit? What were the challenges they faced, and what is their vision for the future? The motivations are as diverse as the individuals themselves. Some are driven by a deep-seated curiosity, a desire to understand the fundamental laws of the universe. Others are motivated by a sense of urgency, a fear of the looming quantum threat, and a desire to protect our digital world from cyber attacks. And some are simply driven by the thrill of innovation, the challenge of building something that has never been built before. Consider Arthur Eckert, a Polish-born physicist who, in the early 1990s, independently discovered a quantum key distribution protocol based on entanglement. Eckert's protocol offered a fundamentally different approach to quantum security, relying on the inherent interconnectedness of entangled particles to guarantee secure communication. He went on to say it was almost like magic, but he would also say it was not magic, it was physics. Or perhaps consider Michele Mosca, a Canadian mathematician who has dedicated his career to raising awareness of the quantum threat and developing post-quantum cryptographic solutions. Mosca understood that Shor's algorithm posed a grave danger to our existing security systems, and that urgent action was needed to prepare for the quantum future. He likened it to preparing for a hurricane. Many of these pioneers have faced incredible challenges, technical hurdles that seemed almost insurmountable. Imagine trying to build a quantum computer, a machine that harnesses the power of individual atoms, using tools that were never designed for such a task. It's like trying to build a skyscraper with Lego bricks. These scientists have had to invent new materials, new technologies, and new algorithms to overcome these challenges. They have had to push the boundaries of what is scientifically and technologically possible. And what about their vision for the future? What do they hope to achieve with their work? Some envision a world where information is truly secure, where privacy is guaranteed by the laws of physics. A world where individuals can communicate freely and securely without fear of eavesdropping or censorship. Others envision a world where quantum technology is used to solve some of the world's most pressing problems, from curing diseases to combating climate change. A world where quantum computers are used to design new drugs, develop new materials, and model complex systems, leading to breakthroughs that would otherwise take decades to achieve. These pioneers are more than just scientists and engineers. They are dreamers, visionaries who are shaping the future of our world. These individuals are turning quantum theory into tangible technology. Their work is shaping the security landscape for generations to come. And it takes a community, a dedicated family, pushing these technologies forward. What kind of ethical hurdles will have to be cleared as quantum entanglement solidifies its place in modern technology? These quantum pioneers, these digital alchemists, have laid the foundation, but what happens when their creation is unleashed upon the world? Unbreakable codes. The very concept has the power to both fascinate and terrify. Are we ready for a world where secrets can be truly kept, where privacy is absolute, where the power to protect information is absolute? Consider the societal impact of such a paradigm shift, a shift that could reshape the very foundations of our governments, our legal systems, and our personal lives. Imagine, if you will, a world where governments possess the ability to shield their most sensitive communications from prying eyes. A world where diplomatic negotiations, intelligence operations, and military strategies can be conducted with absolute confidentiality. This could foster greater stability, enabling leaders to engage in frank and open dialogue without fear of leaks or interference. But what about transparency? What about accountability? What happens when the public is denied access to information that is essential for informed decision-making? What happens when truly unbreakable codes become a tool for oppression, shielding corruption, and silencing dissent? Where does one draw the line? Now consider the implications for law enforcement. Truly unbreakable codes could empower criminals to operate with impunity, shielding their activities from detection and prosecution. Drug cartels, terrorist organizations, and cybercriminals could all use quantum cryptography to communicate securely, plan attacks, and launder money outside the reach of law enforcement agencies. How can we balance the need to protect public safety with the right to privacy, especially when privacy becomes an impenetrable fortress? Is it a problem without a solution? Then there is the question of individual privacy. In a world where data is increasingly collected, analyzed, and shared, the ability to protect personal information is more important than ever. Truly unbreakable codes could empower individuals to control their own data, shielding their medical records, financial information, and personal communications from unauthorized access. One may be asking, isn't that what people should get? Absolutely, but what happens when this power is abused? What happens when individuals use quantum cryptography to conceal illegal activities, to harass or stalk others online, or to spread misinformation and propaganda? Truly unbreakable codes can be a double-edged sword, empowering both the protectors and the perpetrators. What are the ethical considerations? How do we navigate these complex moral dilemmas? One must strike a delicate balance between security and freedom, ensuring that quantum technology is used responsibly and ethically. It is an art that requires careful consideration, ongoing dialogue, and a commitment to protecting both individual rights and the common good. How do we ensure this powerful technology is not misused, that it does not become a tool for oppression or a weapon in the hands of criminals? Perhaps the answer lies in developing robust oversight mechanisms, in creating international agreements that govern the use of quantum cryptography. Perhaps it lies in promoting education and awareness, in empowering individuals to understand the risks and benefits of this transformative technology. Or maybe, just maybe, it lies in recognizing that there is no easy answer, that the ethical challenges of quantum security will require ongoing dialogue, careful consideration, and a willingness to adapt to a rapidly changing world. We might want to consider that this technology can either bring us together or it might pull us apart. Where will it lead us? Only time will tell what else lies around the corner. So we have peered behind the curtain, explored the bizarre and beautiful world of quantum mechanics, and grappled with the ethical dilemmas of unbreakable codes. The question that remains, however, is this. Is quantum cryptography truly the unbreakable code of the future, and is it ready now? The promise is tantalizing. a world where information is shielded by the very laws of physics, where privacy is not a privilege but a right, where secrets can be kept from even the most powerful adversaries. The journey, however, to achieving such a state has been long and complex, filled with both triumphs and setbacks. Let's consider the state of the technology today. Quantum key distribution systems are no longer confined to the laboratory. They are being deployed in real-world networks, protecting sensitive data for governments, financial institutions, and critical infrastructure providers. China's Mikius satellite has demonstrated the feasibility of intercontinental quantum communication, and scientists around the world are pushing the boundaries of what is possible. But there are challenges. Quantum cryptographic hardware remains expensive and complex, limiting its accessibility. Side-channel attacks and implementation loopholes can compromise the security of even the most well-designed systems. And the looming threat of quantum computers, capable of cracking our existing encryption algorithms, casts a long shadow over the digital landscape. Are the rewards worth it? Quantum cryptography offers a level of security that is simply unattainable with classical methods. In theory, if implemented correctly, eavesdropping becomes impossible. This, however, comes at a cost. It requires specialized equipment, constant monitoring, and a willingness to embrace a technology that is still in its early stages of development. What about the competition? Post-quantum cryptography offers a more practical and cost-effective solution, providing new classical algorithms designed to resist quantum attacks. It's like developing new and stronger locks that can withstand even the most sophisticated quantum lockpicks. But post-quantum cryptography is not a silver bullet. It relies on mathematical assumptions that could be challenged in the future, and it may not offer the same level of security as quantum key distribution. Securing the future likely requires a combination of strategies, a layered approach that leverages the strengths of both quantum and post-quantum cryptography. Consider this a digital castle with a quantum vault protected by post-quantum walls, with the best security that can be offered. What about the trajectory? Where is quantum cryptography headed in the next 5, 10, or even 50 years? The pace of innovation is accelerating. Scientists are developing new materials, new technologies, and new algorithms that will make quantum cryptography more practical, more affordable, and more secure. The quantum internet, a global network where quantum computers, quantum sensors, and quantum communication devices are seamlessly interconnected, is no longer a distant dream. It is a tangible goal that researchers around the world are working to achieve. The future is coming, and it is bringing quantum physics with it. While challenges remain, the quantum security era has definitively begun, promising a fundamental shift in how we protect information. While not quite ready for prime time, quantum cryptography is rapidly maturing, and its potential to revolutionize our digital world is undeniable. So the question is not whether quantum cryptography will play a role in the future of security, but how big that role will be. Will it become the dominant technology, replacing classical cryptography altogether? Or will it remain a niche solution, reserved for the most sensitive applications? The answer, like the quantum world itself, is uncertain. But one thing is clear: the quantum revolution is underway, and it is changing the security landscape forever. We are laying the groundwork for the next era of the Internet. Are you ready?